This is Physics 1020 and 1090. The lecture is for Friday, April 3rd. We are in chapter 28 about atomic physics, and this second video for this lecture is going to be about atomic spectra. Suppose you take some hydrogen gas and you enclose it in a container and you heat it up, and it'll begin to emit light. So you let some of the light out, and that's the light that you want to analyze. So the light comes out, and the way you're going to analyze it is you're going to send it to a prism. And the prism, just like when Newton sent white light through the prism, what he got was it split up into all the different colors. When Newton sent the light out, it was a whole rainbow of colors, a continuum of all the colors of the rainbow from red all the way to violet. However, when you do this experiment with hydrogen gas, light coming from hydrogen gas, what you find is, again, you get the different colors, but not all the colors are there. You get discrete spectral lines. You'll get one color, say red, and then nothing, and then you get a green line, and then nothing, and then a blue line. So you get a spectral lines that are characteristic of hydrogen. Now, it turns out that if you put different gases or different materials in here, you'll get a different set of lines. The spectral lines are almost a fingerprint to tell you what atoms you have. So, why study hydrogen? Well, hydrogen is the simplest atom of all. Hydrogen has a nucleus, it's just one proton, and it has one electron orbiting around it. So if you want to understand spectral lines, which can be very complicated, you want to try to start with the simplest system of all, hydrogen. If you can understand hydrogen, you can then maybe have a chance to understand some of the more complicated atoms. So let's look at the hydrogen spectrum in more detail. Remember, visible spectrum in electromagnetic radiation goes from about 400 nanometers out to about 700 nanometers. So this is a function of wavelength along this axis. And what you find is there's one wavelength at 656 nanometers, a bright red line. And then there's nothing, there's no light that comes through all the way through here until you get down to the green part of the spectrum at 486, another spectral line. Nothing, till blue, 434, a spectral line. Nothing until 410, a spectral line. And then you see a bunch more spectral lines here in the very near ultraviolet part of the spectrum until a whole bunch, and then right at 365 nanometers, they end, and there's no spectral lines after that. So that's the hydrogen spectrum, and the question is, what causes that? Well, a Swiss scientist named Johann Balmer actually came up with an equation describing the hydrogen spectrum. Now, the thing is, he didn't get this from any deep theoretical analysis. He got this just from kind of playing around with numbers and looking for relationships. But he found that 1 over the wavelength of the spectral line is equal to a constant r, called the Rydberg constant, times 1 over 2 squared minus 1 over n squared, where n was either 3, 4, 5, and so on out to infinity. So that first red line was 1/4 minus n equals 3, 1/9. So that gave you a certain spectral line. The next line corresponded to n equals 4, so it's 1/4 minus 1/16. And then you go on up and up until you get all those spectral lines that are all crowded together, were all for real large integers, and then they ended when you got out to n equals infinity, which would be 1 over infinity or 0. So when you just had 1/4, that was the end of the spectral lines. Now this quantity here, r, is known as the Rydberg constant, and its value was measured to be 1.097 times 10 to the 7th 1 over meters. So that was a constant that really told you something about the actual wavelength of the spectral lines. Turns out that you can find other families of spectral lines for hydrogen. If you look way out in the ultraviolet or over in the infrared, and you find that the general formula is 1 over m squared, where m is an integer, minus 1 over n squared, where n is an integer, so that you can actually get a general formula for which Balmer is a special case. Well, let me just read you a little bit about Balmer and his spectral formula. This is again from Making of the Atomic Bomb by Richard Rhodes. It says, but no one understood what produced the lines. At best, mathematicians and spectroscopists who liked to play with wavelength numbers were able to find beautiful harmonic regularities among sets of spectral lines. Johann Balmer, a 19th century Swiss mathematical physicist, identified in 1885 one of the most basic harmonies, a formula for calculating the wavelengths of the spectral lines of hydrogen. A Swedish spectroscopist, Johannes Rydberg, went Balmer one better and published in 1890 a general formula valid for a great many different line spectra. The Balmer formula then became a special case of the more general Rydberg equation, which was built around a number called the Rydberg constant. That number, subsequently derived by experiment and one of the most accurately known of all universal constants, takes the precise modern value of 109,677 inverse centimeters. So this was at the end of the 1800s, a big mystery, what caused these spectral lines. Next class, on Monday, we are going to learn about Niels Bohr, who actually derived a mathematical model that precisely described this Balmer spectrum, and he needed to use quantum mechanics to do it.